systems of particles and rotational motion, some more problems are remaining. Let's solve that. Question number 7. Two particles, each of mass m and speed v, travels in opposite directions along parallel lines separated by a distance d. It is given in the diagram. Two particles, mass m, velocity v, they are moving in the opposite directions with a separation distance d. Show that the vector angular momentum of the two particle system is the same whatever be the point about which angular momentum is taken. Here, when we see the angular momentum of the particle 1 and particle 2, okay, both these angular momenta are taken with respect to the point origin. Now we are asked to prove that their total angular momentum is independent of the point about which it is taken. That means we need to prove that the total angular momentum of these two particles is independent of the distance x from origin. That is what we need to prove there. So here we can take the total angular momentum L is equal to L1 plus L2 all brackets. Now that's equal to, we can have R1 cross P1 plus R2 cross P2, because L is equal to R cross P. Then that is equal to, for the first particle, you can see x is the distance. Value of R1 is x, and that is along x-axis, so we can give I cap cross its momentum. According to our diagram, momentum is along negative y-axis, so we can say it is mv, momentum is mv along minus j cap. Plus, come to the second particle. The second particle total distance is x plus d into, that is along x-axis, so I cap cross momentum is mv, that is along positive y-axis, so it is j cap, equal to, we have x mv, then minus sign also we can keep outside, into I cross j, I cap cross j cap, plus x plus d into mv into I cap cross j cap. Now that is equal to, I cross j is k, so minus x mv into k cap plus x plus d into mv, again I cross j is k cap. And now here this bracket we can open, then simplify xmv will be cancelled, so that a total angular momentum you will get dmv k cap. So from this equation we can state that the total angular momentum is independent of x, which means if I take this these two particles at here, these 2 points at a distance d, then also we get the same value of angular momentum, because you can see it depends on d, m and v. So whatever be the distance, if it is x or if it is more than x, whatever be, the total angular momentum is independent of the origin. That is the result we obtain from there. Now come to question 8. A non-uniform bar of weight W is suspended at rest by two strings of negligible weights. Okay, it is given in the diagram. The angles made by the strings with the vertical are 36.9 degree, which we take as theta 1, and 53.1 degree theta 2. The bar is 2 meter long. Total length of the bar 2 meter. Calculate the distance d of the center of gravity of the bar from its left end. Means value of d we need to calculate. Now look at the diagram. The bar is suspended by two strings, and tension is acting there in the string. Okay, in the left one we can take T1, and in the right string T2. Now tension T1 we can resolve into perpendicular components, that is T1 cos theta 1 and T1 sin theta 1. And tension T2 is also resolved into perpendicular components, T2 cos theta 2 and T2 sin theta 2. Okay, so this is the condition. Now in this case we can apply first the translational equilibrium. Okay, translational equilibrium. Translational equilibrium means you can see two cases of translational equilibrium you can observe. One is the forces upward and downward. Two forces are acting upward, T1 cos theta 1 and T2 cos theta 2. And W is acting downward. They are balanced. Similarly, we have two forces acting towards left and right. T1 sin theta 1 towards left and T2 sin theta 2 towards right. So these equilibrium conditions are required so that we can say the rod is in translational equilibrium. We take the second condition now. We have T1 sin theta 1 is equal to T2 sin theta 2. T2 sin theta 2. You know the values of theta 1 and theta 2. You can use sine table. Then you can find a relation between T1 and T2. Okay, or you can take the ratio T1 by T2. So you will get around T1 is equal to 1.33 T2, or T1 by T2 is equal to 1.33 you will get. Then next, use rotational equilibrium. Rotational equilibrium. When you use rotational equilibrium, okay, we need to consider the torque acting there. So here you can see T1 cos theta 1 is trying to pull the left end of the rod in clockwise direction like this. Similarly, the force T2 cos theta 2, the component T2 cos theta 2 pulls the rod, the right end of the rod in anti-clockwise direction like this. So for rotational equilibrium, these two torques should be equal. And you know the formula for torque. Torque is equal to force into perpendicular distance from the axis of rotation. Take the left hand, torque is equal to T1 cos theta 1. That's the force into perpendicular distance from the axis of rotation, that is B, is equal to, now take the right hand, you have T2 cos theta 2. T2 cos theta 2 is the force acting on the right hand into perpendicular distance from the axis. It is 2 meter minus D. Okay. Look at this formula. In this formula, you can substitute the value of T1 there, so that T2 will be cancelled on either side. You know the values of theta 1 and theta 2. Therefore, the only unknown quantity here is T. So you can substitute all other values and you can calculate the value of D. Okay, so next question 9. A car weighs 1800 kilogram. Okay, the weight of the car is 1800 kilogram weight. The distance between its front and the back axle is 1.8 meter. And its center of gravity is 1.05 meter behind the front axle. Determine the force exerted by the level ground on each front wheel and each back wheel. Okay. Now the car we consider like this. So here we can have two tires. Front tires we can take like this. Then the back wheels. And this is the axle. Now the forces we can take like this. Okay. In the first front wheel we can see weight W1 is acting downward. Here also W1. And normal reaction is acting upwards. Normal reaction is also equal, so that also I will mark as W1. The normal reaction acting upward there from the ground. W1. Similarly, here we can have in the back wheels W2. Here also weight W2 is acting on the ground. Ground gives opposite, equal and opposite reaction. So take it as W2. Here also W2. Then what else the data given? Total axle length is 1.8 meter. This distance 1.8 meter, and its center of gravity is 1.05. We can take a point here. 1.05 meter from the front wheels. Now the remaining distance will be 1.8 minus 1.0, 0.75 will be there. Okay, this is the situation now. Again, we need to take a equilibrium conditions. Okay, the total weight, we can take total weight of the car as W, which is acting downward. And for translational equilibrium, total upward force is equal to total downward force. So that is 2W1 plus 2W2. Okay, or from here you can make an equation. W by 2 is equal to W1 plus W2. W1 plus W2. Okay. Now is equal to this W by 2. We can take 1800 divided by 2. So we can take 900. In fact, you need to multiply it by 9.8. Then only actual value you will get, but that we can do at the end. Take it as equation 1. Then next, consider the rotational equilibrium. When you consider the rotational equilibrium, first you will take this front axis. The total force acting in the front part is W1 plus W1, that is 2W1, with the perpendicular distance 1.05. So for rotational equilibrium, we can have 2W1 into perpendicular distance is 1.05 meter. That is the torque acting in the front part is equal to 2W2 into 0.75 is the torque on the back wheels. Okay. Now, what can be done? From here, from this equation, you can find the value of W2. Here 2 and 2 cancel. Then you find the value of W2 from this equation. Value in the sense W2 you will get in terms of W1. Okay. So W2 is equal to W1 into 1.05 divided by 0.75. Now this value of W2 you substitute here so that your equation becomes only in terms of W1. So you will get W1 plus W1 into 1.05 divided by 0.75 is equal to 900. Now simplify the equation, find the value of W1, and whatever value you get, you have to multiply by 9.8, then only you will get the answer in terms of Newton. Once you get the value of W1, substitute the value of W1 in equation 1 and find the value of W2 also. After getting W2, that also you have to multiply by 9.8 so that you will get the answer in Newton. So that is the question. Now, question 10 is not in syllabus. Question 11. Torques of equal magnitude are applied to a hollow cylinder. It is hollow cylinder, you have to know, and a solid sphere, both having same mass and radius. Okay, both are free to rotate. Which of the two will acquire greater angular speed? That is the question. Okay. Now we take a moment of inertia of the hollow cylinder. IC formula is mr square. Then moment of inertia of the sphere formula is 2 by 5 mr square. 2 by 5 mr square. Now we can have alpha angular acceleration. Okay, alpha of cylinder is equal to torque divided by I for cylinder. And angular acceleration of sphere is equal to, both are having same torque acting, divided by Is. So from this, you can see that alpha S, substitute the values, equations of Ic and Is. Then observe the equations, you can see alpha S is greater than alpha C. So sphere has more acceleration. Sphere has more acceleration. At a given time, the sphere acquires greater angular speed. So your answer is sphere. Now come to question 21. Sorry, question 12. A solid cylinder is solid cylinder, mass 20 kilogram, angular speed omega 100 radian per second. Radius of the cylinder is 0.25 meter. Then what is the kinetic energy associated with the cylinder? And what is the angular momentum of the cylinder? Two quantities we need to calculate. Now it is solid cylinder moment of inertia formula is I is equal to mr square by 2. Both m and r are given in the question so that you can find the value of I. Then after getting the value of I, kinetic energy is equal to rotational kinetic energy, only you need to calculate half I omega square. So we have both I and omega are there, so that kinetic energy you can calculate. Then once you get kinetic energy, again angular momentum also you need to calculate. Angular momentum formula L is equal to I omega. You have both I and omega, so that angular momentum you can write it. So direct question. Then next question 13. A child stands at the center of a turntable with his two arms stretched. The turntable is set up rotating with an angular speed 40 revolution per minute. It is given as revolution per minute and speed. But you know, revolution per minute means actually it is the quantity frequency. Okay, so nu is given and nu initial angular speed nu1 is equal to 40 revolution per minute. 40 revolution per minute. 40 revolution per minute. Then how much is the angular speed? Final angular speed you need to calculate nu2. If the child folds the hands, thereby reduces his moment of inertia by 2 by 5 times the initial value. So what is given there? I2 is equal to final moment of inertia. I2 is equal to 2 by 5 I1. This much is the details given in the question in part A. So what you have to do? You have to, here there is no external torque, so you can apply conservation of angular momentum. So I1 omega 1 is equal to I2 omega 2. Now the relation between I1 and I2 is already given there. Therefore, you can have I1 into omega 1 is 2 pi nu 1 is equal to I2. I2 is 2 by 5 I1 into 2 pi nu. Now here I1 cancel, 2 pi cancel, so that you can find the value of nu2, and unit again you have to see we haven't converted the unit, so you will get in revolution per minute only. You get around 100 revolution per minute. Now that is the answer to part A. Now come to part B. Show that child's new kinetic energy, means final kinetic energy, is more than initial kinetic energy. You are asked to prove that. Okay, so we can take the ratio of final kinetic energy by initial kinetic energy is equal to final kinetic energy is half I1 we can take half I1 omega 1. Omega 1 means 2 pi nu 1 the whole square divided by half I2, then 2 pi nu 2 the whole square. So take this ratio, calculate the ratio. When you calculate the ratio, if you are getting a value more than 1, it means final kinetic energy is greater than initial kinetic energy. You will get the value nearly 2.5. It means final kinetic energy is greater than initial kinetic energy. That is our conclusion. Final kinetic energy is greater than initial kinetic energy. Now, how do you account for this increase in kinetic energy? Means what is the source of energy so that the child can increase the kinetic energy? So see here, the child has to do work to fold his hands. So his work or his internal energy is converted to kinetic energy. Okay, the internal energy of the child used to fold his hands is converted to kinetic energy. That is the reason the kinetic energy of the child increases. Now, next question 14. A rope of negligible mass is wound round a hollow cylinder. Remember, hollow cylinder of mass 3 kilogram and radius 40 centimeter. What is the angular acceleration if the rope is pulled by a force of 30 Newton? Also calculate the linear acceleration. Okay, so you can have a cylinder like this. Then a rope is wound around it. Then pull the rope with a force. So what happens? The cylinder begins to rotate. So you can take R as the radius of the cylinder, and this is the axis of the cylinder is the axis of rotation. The force is applied at this edge. Now, what do you have to find? What is the angular acceleration? First of all, it is hollow cylinder, moment of inertia E is equal to mr square. I is equal to mr square. Then torque formula, torque is equal to R cross F is equal to RF sine theta. Here angle between force and this R is 90 degree. So it becomes RF. Okay, we can use capital R because capital R is a perpendicular distance from the axis of rotation. So force is given, R is given. Okay, so torque you can calculate. Once you get the torque, you can use the formula torque is equal to I alpha. I is already calculated from here. Torque is also obtaining from here. So that alpha is equal to torque divided by I. Value of alpha you can calculate. Once you get the value of alpha, we have the relation linear acceleration A is equal to angular acceleration into R. So you have alpha and R so that you can find the value of A, the linear acceleration. Next, question 50. Okay, angular speed of the rotor. Rotor is a rotating object. Okay, rotor is 200 radian per second. Radian per second means it is omega is given. The torque is given 180 Newton meter torque. What is the power required by the engine to rotate the rotor? So correct formula for P is equal to torque into omega. Power is equal to force into velocity. You have studied the last chapter. In rotation, it is torque into omega. Substitute the values of torque and omega and find the value of power. Then next question 60. From a uniform disk of radius r, we have a uniform disk of radius r. A circular hole of radius r by 2 is cut out. A circular hole. Okay, I have drawn in green color. Its radius is r by 2. R is the radius of the disk. It is cut out. The center of the hole is at r by 2 from the center of the original disk. So O is the center of the original disk, and the center of the small disk which is removed is at a distance r by 2. So here at a distance r by 2, O dash. Okay. Locate the center of gravity of the resulting body. So resulting body means the remaining part you can see almost in the shape of a crescent. You can see the remaining part. The green circular part is removed. The remaining part, naturally the center of mass will be okay towards the left hand side. So the center of mass of the remaining body I have marked here as CM2. Okay, that point we can take O double dash. So this is the situation given, and locate the center of mass means you need to find the value of small r. With respect to the original center of mass, where is the position of the new center of mass of the remaining body after the green part is removed? Oh, so how we can find out it? So you can imagine the situation like this. We have two bodies. First one is the disk of green color. Its center of mass is at CM1. The second part is the remaining part, and its center of mass is CM2. When both these objects put together, you will get a perfect disk whose center of mass is at O. And you have studied the total mass of the body is concentrated at its center of mass. So the center of mass of the green disk is concentrated at O dash. So O dash can be considered as a point object. The center of mass of the remaining part is concentrated at CM2 at O double dash. So O double dash is another object. And their center of mass, the center of mass of O dash and O double dash is at O, which is the actual center of mass of the disk. Okay, in that sense, if you can consider this system as a two particles system, as you have studied. What are the two particles? One of the particle is the green disk whose mass is concentrated at O dash, and the second particle is O double dash, because mass of the remaining part is concentrated at O double dash, and their center of mass is the center of mass of the first disk, that is at O, center of mass. So it can be considered as a two particle system. Okay. Now, how to calculate the mass of these particles? That is what we have to see some quantity which is constant here. So it is a disk, a uniform disk. Uniform disk means if you take any particular area, okay, equal areas like this, then its mass will be equal for this 1 and 2. Both the parts having equal mass because it is a uniform disk. Therefore, we can calculate the mass per unit area of the disk. I will write it as sigma, mass per unit area. How to calculate mass per unit area? Total mass of the disk is m, and area of the disk is pi r square. So mass per unit area is m divided by pi r square, which is a constant for a uniform disk. Now let's calculate what is the area of the small disk. Area. Okay, mass of the small disk, which I will call as M1. M1 is equal to mass per unit area, that is M divided by pi r square, mass per unit area into its area. Its area is how much? Pi into r by 2 the whole square. Mass per unit area into area will give mass. Simplify the equation. When you simplify the equation, pi will be cancelled, r square will be cancelled, you will get m divided by 4. M divided by 4. So what is the mass of the small disk? It is m divided by 4. Okay. So what is the mass of the remaining part? M2 is equal to, so m by 4, it is m minus m by 4 is equal to 3m divided by 4 is the mass of the remaining part. Okay, so we assume here m1 is placed, here m2 is placed, and their center of mass is here, and this distance is r by 2, and this distance is R. Two particle systems I mentioned before. Okay, now we take the equation for center of mass of a two particle system distributed along straight line. X is equal to m1 x1 plus m2 x2 divided by m1 plus m2. And it is a homogeneous body. So I can take x is equal to 0. When x equal to 0 is equal to m1. How much is m1? m1 is m by 4. m by 4 into how much distance away? r by 2 plus second object having mass 3m by 4. It is at a distance small r from the origin, divided by m1 plus m2. m1 plus m2 means total mass m. Okay, now equal to 0. All common factors m will be cancelled. Okay, you can simplify like that. And finally, when you simplify this equation, you will get r is equal to r divided by 6. Minus sign also will be there. Okay, r is equal to minus r by 6. What is the reason the negative sign appearing in the final formula? Because you can see the new center of mass CM2 is in the left hand side of actual center of mass O. That is why there is a negative sign. Okay, so study the problem properly. Now, next we have another question. A meter stick. Meter stick means the total length is 100 centimeter. Is balanced on a knife at its center, which means its center of gravity is here, and we can balance its center of gravity because its whole weight is acting through the center of gravity in G. So if you give a support upward here, you can balance the meter stick. Okay, now two coins, each of mass 5 gram, are put on one on top of the other at 12 centimeter mark. Okay, so you take a 12 centimeter mark. There, two coins are placed. Two coins, mass of each coin is given 5 gram. Then the stick is found to be balanced 45 centimeters. So naturally, you see in the left end now the weight is more. So what happens? You cannot balance the bridge at 50 centimeter mark. So you can balance it at 45 centimeter mark. That means if you give a support here now, you can balance it. What is the mass of the meter stick? Mass of meter stick you have to calculate. Okay, now here again we can consider two bodies. One is the meter scale itself. Its total weight is acting through the center of mass here. Capital M, we can take its mass. And the second object we can consider both the coins together. And its weight is acting along the 12 centimeter mark. Okay, which we can write as 2 mg. 2 mg. M is mass of each coin. And both also two forces are acting. One is mg, one is 2 mg, and their axis of rotation, the center of mass, is at the 45 centimeter mark. Scale is now balanced. Scale balanced means torque acting in this direction by this force mg is equal to torque acting in anti-clockwise direction by the force 2 mg with the 45 centimeter mark as the axis of rotation. So now we can apply rotational equilibrium torque on either side equal, tau 1 is equal to tau 2, which means we have torque is force into perpendicular distance from the axis of rotation, mg into 5, because here 50 minus 45 is equal to 2 mg, it is small m, into the difference is 45 minus 2, 45 minus 2. Okay, now so g cancel, can simplify the equation, and small m value 5 gram. So find the value of capital M. You will get the mass of the scale. Mass of the scale is obtained.